Welcome. In Xenon's Glow, the physics of inductively coupled plasma, I explored Xenon's unique glow. Today I turn to Krypton plasmoids, self-contained plasma rings held in place by electromagnetic confinement, to investigate their higher ionization thresholds and resonance behavior. Next up, an animation showing how a single traveling wave oscillation blossoms into discrete standing wave plasmoids, culminating in an exclusive live demo of a stable standing wave plasma ring. Waves ripple a lake's surface, energy moves forward while water stays in place. A sinusoidal wave travels, its points oscillating perpendicular to motion. Amplitude shows oscillation strength, wavelength spans peak to peak, and frequency reveals vibration rate. Next, two transverse waves moving in opposite directions. A green wave travels right and a red wave travels left, both at equal speed and amplitude. As they overlap, crests and troughs superpose, creating an interference pattern that transitions into the standing wave animation. Two traveling waves intersect to form the blue standing wave. Here, energy locks in place, nodes stay motionless, antinodes vibrate at peak amplitude. This shift from motion to structure primes the system for plasmoid formation. Standing wave pulses drive plasmoids in sync. At each antinode peak, 6 stable plasmoids appear. They dim and vanish at zero amplitude, then re-emerge each cycle. This shows that high-energy regions at antinodes create and govern plasmoid formation. A standing wave alternates stationary nodes and vibrating antinodes every half wavelength. Two identical waves, green and red, interfere to form the blue standing wave and plasmoids spaced half a wavelength apart. This is a conceptual model of a high-frequency inductively coupled plasma, driven by a self-tuned Class E MOSFET oscillator at around 10 MHz. An alternating current in the air core coil creates a time-varying magnetic field that induces a perpendicular electric field around the coil's axis. Inside the borosilicate globe filled with low-pressure krypton, this field accelerates electrons, exciting and ionizing atoms to produce sustained plasma glow. As the globe becomes a spherical resonator, standing wave modes emerge, nodes of zero glow and antinodes of peak brightness, revealing resonant eigenmodes of a coupled plasma field system. In top-down antinode diagrams of the M equal to 19 mode, 19 plasmoids circle a central disk. A curved arrow flips each RF half-cycle, showing the oscillating E field. Degree markers confirm that the 180-degree arrow runs tangentially, though it appears radial, along the equator, matching the circulating field. Though 10 MHz implies a 30-meter wavelength, the plasmoids sit millimeters apart. In the near field, fields bind to the globe and plasma, shaped not by free space wavelength but by the system's size, the globe's dielectric boundary, and plasma oscillations, so standing waves scale with local geometry. Crank up RF power and watch the plasmoid ring spin faster. 19 beads drop to 13 as each swells. Packing more electrons raises permittivity and dramatically shrinks skin depth, reflecting RF waves off the dense plasma shell. As permittivity climbs, the M equal to 19 mode's resonance shifts above the fixed drive. The source can't sustain 19 beads, so the plasma hops to M equal to 13, producing fewer, larger beads with noticeably wider angular spans. Emerging higher-order harmonics ripple each bead while leaked RF energy drives rotation. When skin depth falls below the coil radius, bead count falls further and beads broaden, causing the ring to expand outward. At low RF power, the ring supports 19 distinct plasma beads. As power increases, the count drops to 13 and each bead grows larger, revealing how RF power tunes the ring's azimuthal mode. This showcases power-dependent spatial restructuring within the standing wave pattern. In Panel 10, increasing RF power reduced bead count and enlarged each plasmoid. This animation flips the dynamic. As oscillation frequency climbs, Bead count rises from 3 to 11 while each bead shrinks. At lower frequencies, larger beads dominate. Dial up the frequency and new nodes emerge, compressing bead size while increasing mode number. Together, these panels reveal how RF power and frequency reshape plasmoid geometry in opposing ways. Plasmoids flash in sync with the standing wave, appearing at antinodes and vanishing at nodes. As oscillation speed increases, these bursts blend into a continuous glow. This phi phenomenon shows how rapid cycles trick perception, merging discrete flashes into seamless plasma illumination. On the Yaesu FTDX10's 3D waterfall ICP oscillator on pulse at 5 seconds, 23 seconds, and 39 seconds sparks a 10 MHz burst that collapses as soon as the standing wave ring forms. The disappearing spectral line marks energy coupling into the resonant mode and locks the plasma into its bead pattern. As the plasmoids merge, the globe itself becomes a high-Q near-field cavity. RF energy sloshes between coil and plasma with minimal leakage. Krypton's dense plasma shrinks skin depth below the coil radius, turning the ring into a partial Faraday cage. A brief CW noise burst announces ring formation, then falls away, leaving only a steady hum. This panel captures a moment of engineering trust, a video within a video. An iPhone 16 Pro Max, recording in 4K at 120 FPS, hovers 4.5 centimeters above a borosilicate globe. Below, Krypton plasma glows under high-frequency RF. Why does the phone survive? The RF skin depth is much smaller than the coil radius, confining the fields to the plasma ring. Acting as a partial Faraday cage, it traps emissions, leaving the phone untouched and the transceiver in panel 14 oblivious. This shielding stems from the ring's symmetry. In contrast, nonlinear regimes, streamers or toroids, break symmetry and fling fields like sparks. Here, stability wins. It's not just plasma, it's precision. And this glow, caught live, speaks of confinement, shielding, and survivability. Lord Rayleigh's studies in St. Paul's Cathedral showed whispers clinging to curved walls, whispering gallery modes. In optics, WGMRs trap light by total internal reflection in spheres or disks, creating high-Q standing waves. Our plasma globe mirrors this. Its spherical boundary and plasma dielectric response alone shape resonant eigenmodes of nodes and antinodes. Before we wrap up, here's a quick glossary. Feel free to pause and dive into any term.